Hello everyone, welcome to my YouTube channel. Today I'm solving Leetcode question 289, Game of Life. According to Wikipedia article, the game of life, also known simply as life, is a cellular automation device by British mathematician. The board is made up of m times n grid of cells, where each cell has an initial state. Live represented by a 1, or dead represented by a 0. Since this problem statement is pretty long, so I would like to actually take down the main points in case I forgot it while reading through the problem statement. So I take a note. Live represented by 1, dead represented by 0. Each cell interacts with its 8 neighbors, horizontal, vertical, and diagonal. So 8 neighbors. So we used to work on some problem like on the 2D grid, and then they usually mention 4 neighbors, horizontal and vertical. But pay attention, this problem mentions 8 neighbors with diagonal as well. So each cell interacts with its 8 neighbors using the following 4 rules. So we have 4 rules. So basically, those 4 rules, any live cell with fewer than 2 live neighbors dies as if caused by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies as if by overpopulation. Any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. So what does those 4 rules mean? So basically, determine the next state from the current state and then the number of neighbors. So at high level, these 4 rules determine the next state from the current state, and then also based on the number of neighbors. So the next state is created by applying the above rules simultaneously to every cell in the current state, where birth and death occur simultaneously. Given the current state, return the next state. So one keyword here is the simultaneously. All the rules must be applied simultaneously. So what does this mean? If you scroll down to the follow-up question, you can see, remember that the board needs to be updated simultaneously. You cannot update some cell first and then use their updated values to update other cells. So that's what the simultaneous update means. So it's very important to take note on the updating rules simultaneously. So now let's try to take a look at the example. So, okay, so in this first example, so compare the current state with the next state. You saw this 1 has been changed. This one was changed to 0. Why it was changed? Because if you look at all the 8 directions, so in this case, this one actually has 5 neighbors surrounded because it hits the boundary. In these 5 neighbors, it has one live cell. So in that case, look at rule number 1. Any live cell with fewer than 2 live neighbors dies as if caused by underpopulation. So that's why the cell with only 1 live neighbors becomes 0 in the next state, according to the rule 1. So similarly, we can just apply different rules to understand how the current state is changed into the next state. So now let's think about how to solve it. So a very basic and naive approach is, let's say, we create another board to keep track of the next state. Let's say, okay, with the existing board, we have the current state. And then we want the current state to remain fixed because we want to do simultaneous updates. Which means that, okay, so right now, let's say starting from this cell, we update it to 0 for the next state. But when I look at the neighboring cell, let's say when I look at this cell, we still treat the updated cell as its original value 1 because all the updates happen simultaneously. That's what it means. So the naive approach is just to create another board and then use that board to keep track of the next state and then in the end, reassign that next state board to the existing board. So, but that will incur additional memory. It's not going to be very efficient if the board is large. So remember what the first follow-up question said. Could you solve it in place? So without utilizing any additional data structure, how can we solve it in place? So the bottleneck or the challenge for solving this problem is to how to keep track of the current state. Let's say for each cell, if we want to update to the next state, so we have the value of the current state and then we turn into the next state. So how can we keep track of the value for both the current state and then the next state, and then not impacting updating its neighbors? So let's first try to take a closer look at the 4 rules. So I make the table. So basically, directly from the rules, let's say, read from the first rule. Any live cell with fewer than 2 live neighbors dies as if caused by underpopulation. In this case, my current state is 1, is live. And then if the number of neighbors is either 0 or 1, fewer than 2 live neighbors, then my next state is 0, it dies. So I basically keep track of the current state, number of live neighbors, and then the next state. And then for current state, if the current state is 1, any live cell with 2 or 3 live neighbors lives on to the next generation. And then if the number of live neighbors is 2 or 3, the next state is 1, live. Any live cell with more than 3 live neighbors dies, as if by overpopulation. So in that case, basically, if it's greater than 3 live neighbors, in this case, it becomes 0 in the next state, according to rule number 3. And then rule number 4, any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. So the current state is 0, and then the number of live neighbors is 3. The next state is 1. So let's slightly transform this table based on combining the current state and the next state. So for example, for current state 1 and then next state 0, the condition for turning a 1 into 0 is it either has 0 neighbor, 1 live neighbor, or greater than 3 live neighbors. Then the current state 1 will be turned into 0. If the current state is 1 and it has 2 or 3 live neighbors, then the next state would also be 1. If the current state is 0, and then the number of live neighbors is 3, the next state is 1. And then, the unspoken rule is, okay, the current state is 0. It will remain as 0 for the next state if the number of neighbors is not equal to 1, is not equal to 3. So that's kind of how we infer from the rules. So making these tables, so it actually gave us an idea. So maybe we can create a third variable called state. So basically each state denotes each unique combination of current and next. So here, if the current state is 1, next state is 0, then we assign 2 as the value for the state. And then if current value is 1, next value is 1, then we assign value 1 as the state. If current value is 0, next value is 0, then we assign value 0 as state. If current value is 0, next value is 1, we assign minus 1 as state. So in that case, while we keep updating the number of while we keep updating the board based on the number of neighbors and the current state, we can just replace the current state value with the state value. So that's kind of a unique value for each current and the next value combination. So in that case, after traverse through all the cells on the board and finish update and replace the current value with this state value, we can do a second round traversal based on the state value and replace it with the next value. So now let's take a closer look at assign the state value. Why I assign state value this way? So basically for the current value 1, the assigned state value is also a positive integer. And then if the current state is 0, the assigned state value is also 0 or a negative integer. So in this case, I can easily identify if the current state is a live cell or is a dead cell based on if my state value is greater than 0 or less than or equal to 0. So that's kind of how I assign the state value. It's not randomly assigned. It's kind of like create unique combinations of the current and next value. It's also easy to distinguish between the different current states, between the live and dead cell. So now let's start coding. So basically first get the dimensions for m. So m n equals length board 0. Get the number of rows and number of columns in this board. And then we are trying to define a rule update function. So basically this one is going to update from current state to the state value. So let's say in this case, we have the current state, number of live neighbors. So basically the number of live neighbors. So if the current state value is 1, and then the neighbors. So basically, how to determine these neighbors? So we need to determine the number of neighbors based on the 8 direction. So before coding the rule update, let's code up like the code for counting the number of neighbors. So in that case, let's just give the ij, and then we kind of make this one 2-step. Count number of neighbors. So given index ij, we want to count the number of number of living neighbors. So basically in 8 direction. I plus 1j. Okay, so let's actually do the directions outside. So directions equals 1 minus 1 minus 1 0 0 minus 1 0 1. So I first list the move to get to the 4 horizontal and vertical neighbors, and then let's take a look at the move to get to the diagonal neighbor. Okay, so all 8 directions. Basically for x, for di, dj in directions ni, nj equals I plus di, j plus dj. So basically get the indexes of neighbor. And then check if the neighbor is a live cell or dead cell. If board ni, nj equals 1, then we increase our count. So in that case, let's keep a count variable, initialize it to 0. So if it's a live cell, if the neighbor cell is a live cell, then we increase our count by 1. So in that case, we count the number of living neighbors for index I and j. And then the second step, we update from the current state to the state value we already determined. So if board I, j equals 1, if the current value is 1, and then if the number of neighbors, if count less than 2 or, okay, sorry, I made a typo here. So here it should be greater than 3. Greater than 3. In that case, the board I, j equals 2. Okay, so now let's take a look back at the logic for counting the number of living neighbors. So I'm checking, in this condition, I'm checking if the board value equals to 1. So what if this the neighbor has already been updated with the new state value? So in that case, this logic doesn't make sense. So it will miss a lot of cases. So in that case, I will just do if it's greater than 0. So this will work even after I update the value on the board to the state value. Let's continue coding the update from current state to the state value. So if current equals, if 2 less than, sorry, if count in 2, 3, my board I, j equals 1. So basically, I'm just coding based on this table I created beforehand. So basically, I'm checking the current value, which is the board ij, and then doing the updates. If board ij equals 0, and then if count equals 3, in this case, board I, j equals -1. Else board I, j equals 0. So now I realize there might be a problem with that. So, well, yep. So, cool. So we finished coding the logic for counting the number of living neighbors, and then also update from the current state to the state value. So now we just return this one. Actually, we do not need to return because we do the update in place already. So in that case, we're just going to loop through every cell on the board and then trying to do the update. And then, so basically in this loop, we update from current state to state value. So now we need to update from the state value to the next state. So we need another for loop. And then we need another function to do the reverse mapping. Define state to next. So in that case, let's try to basic import I, J equals import ij in, I'm trying to look at my table. So the next state value 0 requires the current state to be either 2 or 0. Else board I j equals 1. So when the current state value is 2 or 0, the next state, when the state value is 2 or 0, the next state is 0. When the state value is 1 or minus 1, the next state value is 1. So then we just loop through the board again and then update to the next state. Okay, so this is our solution. Let's try to run the test case. Oh, this index out of range. So here I need to check if they are within the range. So if 0 less than n. So basically they have to be within the boundary of the board. Okay, we passed the test case. Let's try to submit it. Okay, cool, awesome. So this is the end of my video. If you like my video, please don't forget to subscribe to my channel. Thank you.